Right now, somewhere on Earth, a clock is counting. A second passes, then another. You've never once doubted that a third will follow. But somewhere in the far future, trillions of years from now, in the last flicker of a dying cosmos, physicists suspect that assumption may fail. Not slow down, not fade, fail. There may be a final second, a tick with no talk after it, and once you accept that possibility, an even stranger question forces itself into the room. If time can stop, was it ever really moving to begin with? This isn't a thought experiment for late-night dorm rooms. It's a live question inside some of the most respected physics departments on Earth, and one physicist in particular, Roger Penrose, who shared the 2020 Nobel Prize in Physics for his work on black holes, has proposed an answer so strange that most people's first reaction is disbelief. Before we get there, we need to understand why physicists think time might end at all, and the answer starts somewhere you'd never expect, inside a cup of coffee. Why physicists suspect time has a direction and a limit. Watch a cup of hot coffee sitting in a cold room. The heat leaves the coffee and spreads into the air. The coffee cools. The room warms imperceptibly. Now here's the part that should bother you more than it probably does. That process never runs backward. The room never spontaneously cools further to reheat your coffee. Never once in the history of the universe, as far as anyone has observed. In the 1800s, physicists studying steam engines gave this one-way behavior a name, entropy. Loosely, entropy measures disorder, how spread out and mixed up energy has become. And they discovered something that still ranks as one of the strangest laws in all of science. In any closed system, entropy only increases. It never reverses on its own. This single rule may be the real reason time has a direction at all. Not some invisible river carrying us forward, but simply this. Disorder spreads, and it doesn't spontaneously unspread. You remember yesterday because yesterday had lower entropy than today. You don't remember tomorrow because tomorrow statistically will have more. Physicists call this the thermodynamic arrow of time. And once you take it seriously, it leads somewhere unsettling. If entropy always increases, it should eventually max out. Every star will exhaust its fuel. Every black hole will slowly radiate itself into nothing through a process called Hawking radiation. Every last scrap of usable energy will spread into a thin, cold, featureless fog. Physicists have a name for this final state: heat death. Picture the universe as an enormous, silent room. At first it's full of contrast. Blazing stars next to freezing void, dense galaxies next to empty gulfs of space. Heat death is what happens when all of that contrast finally, completely dissolves. Every temperature becomes the same temperature. Every location becomes indistinguishable from every other. Nothing flows because there's nothing left for anything to flow toward. And here's the question that should stop you cold. In a universe where absolutely nothing changes ever again, does time actually continue, or has it, in every way that matters, already ended? The first ending, when the universe runs out of events. This is where physicists start to split. One camp argues that time technically keeps ticking even in heat death. The equations of physics don't demand a hard stop. Particles still exist, at least in principle. If you could somehow keep a clock running, it would still, mathematically, tick forward. But here's the deeper problem. Many physicists and philosophers of physics argue that time isn't actually measured by some hidden universal clock at all. It's measured by change, by events, by one thing becoming a different thing. If nothing ever changes again, no particle collision, no photon absorbed, no atom decaying, then in what sense is time still passing? A universe with zero events happening for the next trillion years is, for every observer inside it, indistinguishable from a universe where time has simply stopped. It's a bit like asking whether a movie is still playing if every single frame, forever, shows the exact same image. Technically, the projector might still be running, but nothing you could ever call a story is happening anymore. This is where Roger Penrose looked at the exact same heat death scenario and saw something nobody else had noticed. Penrose's turn, an ending that looks suspiciously like a beginning. In the far, far future, Penrose pointed out, the universe will be dominated by one thing: light. Massless particles, photons, stretched out by the relentless expansion of space until they carry almost no energy at all. And there's a genuinely bizarre fact about light, confirmed repeatedly through Einstein's special relativity. For anything traveling at the speed of light, no time passes at all. Zero. A photon, in its own frame, experiences the entire multi-billion-year history of the universe in a single instant. So Penrose asked an audacious question. If the far future of the universe becomes dominated by particles for which time and scale essentially stop meaning anything, might that state be mathematically identical to the far past, the unimaginably hot, dense beginning of a universe where scale and time were also in a sense meaningless? This became his theory of conformal cyclic cosmology, or CCC. In it, the infinitely stretched, cold, featureless end of one cosmic era becomes, through a kind of geometric sleight of hand, indistinguishable from the infinitely compressed, explosive beginning of the next, not through magic, not through mysticism, through the underlying geometry of space-time itself, when you strip away every notion of physical scale. I want to be completely honest about where this stands scientifically. CCC is a hypothesis, not an established theory. It makes a genuinely testable prediction: faint circular patterns in the cosmic microwave background. the ancient radiation left over from the Big Bang, which Penrose and a collaborator claimed to detect. Other cosmologists reanalyzed the same data and found the pattern statistically indistinguishable from noise. The debate isn't resolved. Most cosmologists remain skeptical, but CCC remains one of the few mathematically rigorous attempts to ask what genuinely happens at the most extreme possible limit of time, and to suggest that maybe the end isn't a wall, but a seam. Heat death is the slow ending, but there's a second, far more violent one, and it's hiding inside every black hole in the universe. The second ending, where the equations simply give up. Fall toward the center of a black hole, and general relativity makes an extraordinary claim. Past a certain point, every possible direction you could travel, literally every path through space, leads inward toward a single point called the singularity. Here's the part that sounds almost like science fiction, but is a rigorously derived consequence of Einstein's equations. Near the singularity, space and time effectively swap roles. Moving forward in time becomes just like moving forward in space, unavoidable, undeniable, a direction you cannot choose to reverse, the same way you can't choose not to reach next Thursday. And at the singularity itself, the mathematics doesn't slow time down. It stops producing meaningful answers at all. Density becomes infinite, curvature becomes infinite. Time, as a concept the equations can describe, ends. But, and this matters enormously, almost no physicist believes this literally means time philosophically stops in some cosmic sense. What it really means is that general relativity has been pushed past its limits. Infinities in physics are usually a signpost, not an answer. They mean your theory has left the territory where it actually works. This is exactly why physicists have spent decades hunting for a theory of quantum gravity, a deeper framework that could replace that breakdown with something finite, something that actually makes sense. And chasing that goal has led to one of the strangest ideas in modern physics, that time itself might not be smooth at all. It might be made of pieces. Is time made of grains? Some approaches to quantum gravity, loop quantum gravity among them, propose that time can't be divided infinitely. There may be a smallest possible unit, called the Planck time, roughly 10 to the negative 43rd of a second. Below that unimaginably tiny scale, before and after may simply stop being meaningful concepts. It's a bit like asking what lies north of the North Pole. The question feels normal grammatically, but it assumes a structure, further north, that at that exact point no longer exists. If this picture is right, time doesn't end the way a river hits a dam, all at once, with a wall in front of it. It ends the way a film strip runs out of frames, except there is no frame beyond the last one, not because something is blocking it, but because beyond has stopped being a coherent idea. I need to be clear here too. This is speculative. Quantized time has never been experimentally confirmed. It's one of several competing approaches to quantum gravity, alongside string theory, which handles the same problem completely differently, keeping space-time smooth and continuous but adding extra hidden dimensions instead. Physicists are genuinely divided on which approach, if any, is correct. Nobody has directly observed evidence of quantized time, but if grains of time are real, it suggests something enormous, that time isn't some external river we happen to be floating on. It's something built, an emergent property, the way temperature emerges from trillions of jostling molecules, even though no single molecule has a temperature of its own. No single Planck scale tick has time. Time is a pattern that only appears once you zoom far enough out to see it. And that idea opens the door to the strangest possibility of all, one that Einstein himself couldn't fully shake. What if time was never flowing at all? This is the block universe view, and it comes directly out of special and general relativity. In this picture, the past, the present, and the future all exist, permanently, equally, all at once. The same way every page of a novel exists simultaneously on a shelf, even though you experience the story one page at a time. Your first heartbeat, this exact sentence you're reading right now, and the final moment of your life aren't separated by some river of time flowing past you. They're simply different locations fixed along a structure. The same way Tokyo and Rome are different locations laid out across space, not flowing past one another. If this is correct, asking can time stop becomes a bit like asking can East stop. It's not that the question is stupid, it's that it's built on a hidden assumption that doesn't hold. Time, in this view, isn't a process happening to the universe. It's a dimension the universe already has, in full, front to back, the way a book already contains its final page the moment it's printed. Under this interpretation, heat death isn't time running out. It's simply the last page, a page that has existed in exactly the same sense since the very first page describing the Big Bang. Nothing arrives at it. It was always there. This remains deeply controversial. Some philosophers of physics insist that our vivid, undeniable experience of now, that unmistakable sense of moving forward, must correspond to something real, something the block universe struggles to explain. Others argue our sense of flow is simply the brain's trick. Memory stitching together static moments into an illusion of motion, the same way a film reel of still images creates the illusion of movement on a screen. Nobody has settled this. Not physicists, not philosophers. Not even Einstein, who once wrote to the family of a recently deceased close friend that the separation between past, present, and future was, in his words, only a stubbornly persistent illusion. So, can time actually stop? We started with something so obvious it felt beneath questioning that time simply continues, tick after tick, forever. Look closely enough, though, and that certainty dissolves into one of the strangest open territories in modern physics. Heat death may leave the universe with nothing left for time to measure. Black hole singularities may reveal not that time literally halts, but that our best theory of gravity has run out of road. Quantum gravity may reveal that time isn't continuous at all, but built from indivisible grains too small to picture. And the block universe may reveal that the entire question rested on a misunderstanding, that time was never flowing in the first place, only appearing to. Roger Penrose's own answer might be the boldest of all, that the ending isn't an ending, that the coldest, emptiest, most stretched out future a universe can reach is mathematically identical to the hottest, densest, most explosive beginning a new universe can have. That endings and beginnings, once you strip away every notion of scale, might turn out to be the exact same shape, viewed from two directions. We don't know which of these pictures is correct. Possibly none of them are, and the real answer is sitting quietly in an equation no one has written yet. But maybe that's the real discovery hiding inside this question. We spend our entire lives treating time as the one thing in the universe we can always count on. Steady, obvious, unquestionable, and yet the closer physics looks, the less obvious it becomes, and the more it starts to resemble something built, something emergent, something that, under the right conditions at the far edge of everything, might come undone. The deeper we look into the universe, the more it begins to look back at us.